difficulties while designing the background learn in our class. So in today's class, we are discussing radial basis function. How it is different from your conventional neural network. What are its advantages? How this radial basis function transferring the data from input layer to output layer. They are different. Which are the learning in today's class. So before moving to radial basis function, before learning radial basis function, let us review how perceptron of a single layer neural network is coordinated and training up and giving you the output. In the figure, you can see the architecture of perceptron with one layer of variable connections. Different views. Here, we are able to see the architecture of perceptron with one layer of in different views. So the leftmost figure is indicating how your human eye is scanning the information. Human eye is scanning the information. See here, the lens is correcting the picture. The lens is correcting the picture. This blue structure, big blue circle is indicating. Then the picture is projected on retina. Static weight corrections for the input neurons. So these input neurons will be processing your information with the trained weight corrections. Trained weight corrections. Then the information is processed single output neuron. Best example for single layer perceptron neural network. Here you can see, you can visualize the picture. The lens will be focusing on the image, the lens of your eye. So the picture is projected on retina. So the information is transmitted via the input neurons to output neurons with the trained weighted connections. Trained weight connections. So this picture is indicating. This picture on the right top is indicating fixed weight layer using different designs of functional description of neurons. Okay, the right side upper part picture is indicating fixed weight layer using defined designs of functional description of neurons. So here, the bottom right picture. There is no weights indicated here. The fixed weight layer will no longer be taken. Here, I1, I2, I3, I4, I5 are indicating input neurons. And sigma is indicating as output neuron. Best example for understanding single layer perceptron neural network. The information is gathered from the lens of your eye and projected on retina, where static weight connections for different input neurons are present. Interaction of different many number of neurons will be processing the information with the trained weight connections. The information is processed from input neurons to the output neurons. So single layer. Here there is no hidden neurons. Okay. Whereas in your radial basis function neural network, it has only three layers: input layer, hidden layer, and output layer. Just as we have seen in the back propagation algorithm, each layer, interaction between each layer, input layer, hidden layer, weights are mentioned and you are evaluating the weights also. But here, specifically in RBF system, my voice audible? Yes. Specifically in RBF system, the information is processed, just transmitted from hidden layer, from input layer to hidden layer. No weights are considered in the radial basis function. No weights are considered in the yes, is my voice audible? Please respond. The RBF network, radial basis function. The connection to hidden neurons are not weighted. They only transmit the input. You will not consider any weights from input layer to hidden layer. So we can this neural network layers, also known as multiple layer perceptron neurons. The input neurons are indicated with the small a. Hidden neurons are called H and output neurons are omega. See the structure of radial basis function. It is complex. The structure of this radial basis function is a bit complex. Also simple because it will not consider any weights in the information processing from input layer to hidden layer. So it is the computation becomes simple. Yes. Is my voice audible? Please respond. No one is responding. Yes. No. So, like your perceptron, single layer neural network, radial basis function neural network is also built in layers, but it has exactly only three layers. Exactly only three layers. Okay, one input layer, one hidden layer, and one output layer. So in perceptron networks have feed forward structure. Their layers are completely linked to each other. Here in RBF, the input layer does not participate in information processing. RBF networks are like multi-layer perceptron universal function approximation. So before going to how your RBF network actually in existence, what is the difference between RBF network and perceptrons? The difference is in information processing and computation rules within the neuron lying outside of your input layer. Okay, observe the difference here. The difference between perceptron neural network and RBF neural network is in the information processing and in the computational rules. How the computational rules, that is, we are calculating weights. In the back propagation algorithm, we have seen we are calculating weights in each stage, and at the output stage, we are verifying whether the desired value is reached by checking the difference between desired target value and desired value. If that error is minimum, you are not going for back propagation. But if you want to reduce that error, definitely you need to retransmit the error from output neurons to input hidden neurons and also input neurons. Okay, the information processing, and you need to calculate all the rules within the neurons lying outside of input layer. So in the what are the main components and structure of RBF network? RBF network output neurons contains only identity as activation function and one weight sum as propagation function. So here we are not going for considering or adding up all the input values and outputting the sum. So the output response is simple. Okay, it need not take all adding up all the inputs and outputting the sum. That process is absent in your RBF network. Hidden neurons. Hidden neurons are also called as RBF neurons because they are located in the radial basis function layer. So as the propagation function, each hidden neuron receives a normal value. Normal value that calculates distance between input into the network and so and the position of your neuron. Okay, it is calculating the distance between input into the network and the position of neuron, whether it is center or not. So this is entered into radial activation function, which calculates and outputs the activation of the neuron. So here you have radial basis function input neuron, center of radial basis function neuron, and RBF neuron, and RBF output neuron Finally, RBF network. Okay, RBF network. So from the basic definition of single layer perceptron neural network, the input neurons for radial basis function are also same. Okay, here you can see the definition for input neuron. An input neuron is an identity neuron. It exactly forwards the information received. It represents the identity function, which should be indicated by a symbol like this. So input neuron is represented with the backslash symbol. Input neuron. Okay. Function is indicated with backslash symbol. The input neuron is represented with a circle with this backslash. Okay, that is your input neuron. Input neuron defined both for perceptron neural network and RBF neural network are also the same. Both the cases it is the same. So when you are considering the RBF neuron, okay, how define center of RBF neuron? You may be asked like this. Define center of an RBF neuron. It's the point in the input space. The center of an RBF neuron is H is the point in the input space where RBF neuron is located. The closer the input vector to the center vector of RBF neuron, the higher is its activation function. The higher is its activation function. So that is indicating your center of RBF neuron. Next, RBF neuron. The so-called RBF neuron has propagation function, which determines distance between the center of neuron and your input vector. So that this distance between center of the neuron and input vector represents the network input. So again, from this, the network input is sent through radial basis function, which outputs the activation or outputs of the neuron. So usually, RBF neurons are represented like this: circle with the symbol of normalizing of C, X divided by Gaussian B. Gaussian B is indicating here activation function. RBF output neuron. RBF output neuron is indicated with omega. Using here in the output layer, there we are using weight sum as a propagation function and identity as a activation function. So they are represented by circle with sum and backslash. Next, RBF network. How RBF network is defined? So an radial basis function network has exactly 3 layers. Okay, the input layer consists of input neurons. Hidden layer consists of RBF neurons, not your hidden neurons. Okay, RBF neurons, and the output layer consists of RBF output neurons. So each layer is completely linked with the next following one. So here RBF network. this RBF network. This symbol is indicating your input neuron. Okay, circle with the backslash line. And input neurons. This one is indicating your RBF neuron or hidden neurons. Okay, there you can see C comma X, normal of C comma X, Gaussian B. Okay, activation function you are using is Gaussian B, and your output is weight sum of all the neurons, information received by all the RBF neurons. Okay. So how your RBF network is defined means the RBF network has exactly 3 layers. Okay, the input layer consists of input neurons. The hidden layer, also known as the RBF layer, consists of RBF neurons. Output layer consists of RBF output neurons. So how your RBF network receives the information and how it is transmitted. Information processing of RBF network. The RBF network receives the input by means of unweighted connections. Then the input vector is sent through norm so that the result is a scalar value. Okay. Only positive due to the normal value. This scalar value is processed by radial basis function. For example, by Gaussian bell. Okay, Gaussian bell. The outputs of different neurons in the RBF layer or different Gaussian bells are added within the third layer. So Gaussian bells are related to whole input space are added here. So in the we are doing the same process for second, third, and fourth RDF neurons, which are differently located. So each of these neuron measures another distance from input to its own center and provides different values to your output neuron. So these values are simply accumulated in the output layer. So it is easy to understand that any surface can be shaped by dragging, compressing, and removing Gaussian bells and subsequent accumulation. So here the development terms for superposition of Gaussian bells in the weights connection between RBF layer and your output layer. Okay. So how this information is processed in the RBF network by using normals and radial basis functions only. Okay, the information is completely processed by using your normal values and radial basis functions. So here in the network, they have considered an example 141 RBF network. That is, it represents a one-dimensional output. Yeah, one-dimensional output. So, which can be represented as a function. So, additionally, the network includes the centers, the 4 inner neurons, H1, H2, H4, and therefore has Gaussian bells, which are finally added at the output neuron. So network processes 4 values, row 1, row 2, rho 3, rho 4, which influences the width of your Gaussian bell. The height of your Gaussian bell is influenced by weights. Since individual output values are multiplied by those weights, you need to go for summation. Different Gaussian bells in one dimension. RBF neurons are added by an output neuron of the RBF network. So the Gaussian bells, the activation function, Gaussian bell is nothing but your activation function have different heights, widths, and positions. So one of the example you can see. Okay. See the position change in the output for different Gaussian functions. Gaussian 1, it is at right. Okay, Gaussian 2, it is moving to the other corner. Okay, next Gaussian 3. It is also slightly away from your y-axis. And the fourth case, it is completely on the opposite side. So sum of all these four Gaussian bell functions, the resultant graph is mentioned. So here you need to bother about the width and height of your Gaussian function. That is very important. And also you need to calculate the distance. Okay. Here they have mentioned an example. You can go to the example. How the distance is calculated using the formula. RH is equal to norm of x minus c h. Here the norm is used to calculate the distance between input vector and center of the neuron. So different number of calculations are involved. But this RBF network is more quickly it acts. It gives accurate results. At the same time, it will be acting very quickly when compared to your back propagation. Here they have mentioned the distance. Okay. So up to this point, you can write that is enough for your examination point of view. What are the different layers in your RBF network? How the neurons, input neuron, hidden layer or RBF layer, and output layer, how the information is processed. You should draw this basic architecture and we are using norm and Gaussian bell function for your RBF network, that is your hidden layer. And at the output point, you are summing up all the outputs from your RBF layer and giving you your desired output response. So in multi-layer neural networks, there are other varieties also in existence. Presently, researchers in the area of neural networks, they are studying or learning or applying the deep learning neural networks. Multi-layer deep learning neural networks. where the layers are subdivided into small subnetworks. That's all for today. And in tomorrow's class, we shall continue with associative memories. If you have any queries, you can ask me now. This third unit is a bit complex, but if you are learning, it will be simple and easy for you when you are doing your project works. Maximum people need to utilize either neural networks or fuzzy logic for your project work in 4 to 6.